before we start, let me just make an announcement. We have another kind of a guest lecture, I called it, although it is actually not part of this course. But since Baz and Maurice are also teaching assistants, and you, when you went to the practice, you probably realized that they are really, wait, here we go. That they are very experienced with graphics, so they really know a lot about programming. They giving a talk, and it is actually targeted also towards the game bachelor students. And this is why I kind of wanted to announce it as a guest lecture, but of course it's not part of the official course and not part of the exam. But you're very much welcome to go there. It is they have been to the Game Developers Conference earlier this year in San Francisco, and they want to give a report about that, about the new graphics techniques that they saw there, about recent developments that we have in computer graphics, especially in games, but also in general, of course, in computer graphics. And so the idea is that they tell you a little bit about what kind of techniques exist and how they generally work. So you get like an intuition about the techniques that are used commonly now in modern games, the advanced techniques. So it will be a more high-level description, so they will not talk about how to implement it concretely, and they will also not go into the mathematical details. So don't worry if you don't like the mathematics here. You can, of course, go to the course, and but I think for the students who are in this course, it should be quite interesting, and you should be able to understand most of it. Although it is called advanced computer graphics, so as I said, they explicitly want to make it in a way that the students from this course who are interested in more information about graphics, that they can go there. So I highly encourage you, especially the ones among you who always complain that this course is has too much of a basic character and only scratches the surface. This is a chance now for you to get more detailed information about more advanced graphics. Yeah, so they have a couple of things that they saw there that they want to talk about. First, they want to give a quick introduction about their scholarship, because they got funding to go there, which might also be interesting for some of you, of course, for future conferences. And then they will talk about a few techniques. One of them is actually related to something we also have in the third programming assignment, so it should be very interesting, especially for the people who want to implement that. But as I said, it's not official part of the course, so if you don't want to go, you should not run into problems with the exam. But as I said, it is very interesting, I think. So I will definitely go there. I'm curious to see. So these are two examples that they have from techniques that they want to talk about. Oops. Yeah. All right. And if this doesn't motivate you, then there are drinks in the break. Maybe that. Yeah. So yeah. And yeah, like I said, it's not mandatory, but it's highly recommended. And the talk will be in English. So for the GMT students, the international GMT students, don't worry, you will hopefully understand it. There was a question somewhere there? Yeah. Yeah, I realized that this is actually pretty bad scheduling, that I encouraged you at the beginning to go to the tutorial, and now I encourage you to go to this talk. The only thing I can say is the same tutorial is on Tuesday, so go to the Tuesday tutorial. Now, the really bad scheduling is that on Tuesday there is no lecture and there is the DC Dark Game Jam. So if you pick both of them, if you decide to go there and to the Game Jam, then it's really, you will miss one of the tutorials. So that is indeed a problem. And but I don't really know how to change that, because it's also not that easy to get a room out of time. So yeah, you really have to make the decision. If you don't go to the Game Jam, then go to the Tuesday tutorial. If that doesn't work out, then you have to decide what is more important for you. Yeah, sorry for the conflict, but there's nothing we can do about it. But nevertheless, I think it's kind of a nice thing to have this additional talk. So I'm quite happy that they want to do this, because it kind of gives you a little more information. So even I think for the students who are not that much, yeah, how do I say that? it's not only for the graphics hackers, so also the other people. I think it would be quite interesting to see what's the current what are the current hot topics in graphics. All right, yeah. So advanced computer graphics, but shadows is actually also one of the more advanced topics. For example, it's not really covered very well in our book, which is about the fundamental of graphics. So you see, it's kind of more an advanced topic, but it is actually a quite important topic because shadows really add a lot of information, a lot of realism to our images. So this is a photo that I actually got from the book, which is from the chapter on visual perception. And you see here, of course, the perception of these two images, of these two scenes, which are exactly the same with one exception, which is the shadow, is completely different, because in the bottom it looks completely like a completely different scene than at the top, although the only thing that changes is really the shadow. So I think this is a convincing example why shadows are important. Now for shadows, we usually distinguish between two types of shadows. One is the so-called hard shadows, where we have a hard border. So if we look here, you see here that when we move from the light to the shadow, it's just one step and then we're in the shadow, so it's dark or it's light. Whereas here with the so-called soft shadows, you see that you have a smooth transition from the light to the shadow, which is the more realistic scenario, of course. And if you look at it from the image, I actually realize it's not such a... Where's my mouse pointer? Here it is. It's not such a good image, but it kind of illustrates the idea. So if you have a light here, then of course everything on top of this object here is in the light, but here no direct light hits this area, so this is then the shadow. And in graphics we usually call this object an occluder, the object that produces the shadow, and the object that where the shadow falls onto is called the receiver. Now for soft shadows, you see if you have a bigger, you can imagine that if you have a bigger light, then the light here, the borders here are not strict, because here at the part here you see there is light coming in, but from that side there is not as much light coming in. So this area receives all the light, this area receives only a little light, and this area receives no light, which is why we have these soft borders from the shadows here, from the soft shadows here, or the soft borders in reality when we have natural light. And in graphics we call this area here that is completely in the shadow the umbra, and the parts that are here partly in the shadow we call the penumbra, and of course everything else is then in the bright light. So for the lecture I will only look into the hard shadows, because modeling shadows is actually not that easy, and so I will only describe three methods, or one method in detail, and two I will only mention about hard shadows, and then I will just make a short comment about the soft shadows. One of the approaches for hard shadows, which I will only shortly mention, is shadow maps, and the reason why I'm only shortly mentioning it is that this is also part of the programming assignment. I think it's one of the medium tasks, so if you're interested in this, then you're very welcome to gain more knowledge into it. But for the rest of you, if you just know the rough idea of it, that is enough, because I'm not going to explain more. And the idea of shadow maps is basically that you have a light source and you have a viewpoint, and you want to know where the shadows are. And what you do is you treat the light source as another viewpoint. So let's call it E dash. If our viewpoint is E, then let's call the light source another viewpoint, E dash. And then you're modeling the scene in the same way as if you would draw this projected towards the light source, towards this new viewing vector. And then you fill the set buffer of this scene with the set values like you would model the scene, which means you will fill it with the set values of the closest object. So here you would get the set value of the green object in this set buffer. So we're only interested in the set buffer values. Now the next step is that you do, of course, the real modeling from the viewpoint E, and then you also fill, as part of this, you also fill the set buffer, of course. So you have two set buffers with two set values, and what you do now is you do a transformation of this coordinate system into the light source coordinate system, and we know how to do that. This is just a transformation from one coordinate system to another one. And then we have two set values here. We have the set value set dash, and we have the set value set here from this perspective. But, oh, that is stupid. We have the set value dash, and we have the set value set. Let's call it set star, because that is this set value under this transformation here. So this is the set value that is comparable with this coordinate system. And then we look into these set values. If this set value is smaller than set star, we know that the object, the closest object to the camera, is behind the closest object to the light source. And that means, of course, this object is behind this object with respect to the light source, which means it doesn't see the light, which means it is in shadow. So what we do is when we draw this scene, we transform that set value, compare it with the set value with respect to the light source. If it is larger than the light source set value, then we draw it in shadow. If it is the same, then we know that it is hit directly from the light source, and that means it is enlightened. It's not in the shadow. The reason why I was hesitating now is I'm not sure if larger or smaller. I think that depends, of course, if we look in the positive or the negative set direction. But yeah, of course, you're able to figure that out yourself. That is pretty much the convention. If you're looking in the positive or the negative set direction, then it is the larger or the smaller set value, of course. So the one that is further away, depending on your convention. All right, yeah, so that's the basic idea of shadow maps. It's the basic idea is pretty simple. Of course, the implementation is a little more difficult, and that is then what you're very welcome to do as part of the practical assignment. The approach I want to cover in a little more detail is these so-called shadow volumes. And in the shadow volumes, we have we're treating shadows as volumes, and then we calculate the shadow condition based on these volumes. So what we have is we have a light source here. We have occluder objects that produce a shadow, and they produce a shadow volume. We treat this shadow as a volume in our scene. So if you look at this in 2D, the volume, the shadow volume is this the silhouette of this area, this colored area here. So you see here the red object has a light red area here. The blue object has a light blue. Okay, where they overlap, of course, it's purple. And in 3D, this is like a cone, or actually a part of a cone where the top in front of the occluder is cut off. But you see that this can be seen as a volume. And the idea of this, this volume is then described by faces and normal vector, and if that is facing to the outside, no. And they are, with respect to the cameras, they are either front or back facing volumes then, depending on the normal vector. Remember we had this with backface culling, the same when we looked at the back or at the front of a polygon, and in this case we're looking at the front or the back of the face of this silhouette of this shadow volume. And the idea now how to calculate the shadow is actually pretty much related or pretty similar to this very simple polygon test when we want to test if a point is inside of a polygon. And the test is that we just take the point and shoot a ray in a random direction. So for example in this direction, and then we count how often it hits one of the vertices of the polygon. If this is an odd number, then the point is inside. If it is an even number, then it is outside. So you can see that if we're going from here, no matter where we shoot, if we shoot a ray, we will always get an odd number of vertices that we intersect. So it will always be odd, the number of intersections, which means it is inside. If it is outside, no matter where we shoot, we will always get an even number of intersection. There is actually the third case where we have something that is array that shoots directly along a vertex, but since that doesn't intersect, you can either not count this as an intersection, then you have again two intersections, so an odd number, which means it is inside, or you just shoot another array that doesn't intersect with a vertex, and then that doesn't lie on a vertex, and then you have your result. So this is I think pretty straightforward, and this is basically the same idea that is used here for the shadow volumes, only that we're not counting here how often we cross a vertex, but we also have to consider when we go into and out of the shadow volume. And of course you can imagine if you enter a shadow volume but you do not go out of it, then you are of course at the end still in the shadow. If you enter a shadow volume and go out of it, then you're not in the shadow anymore unless you entered another shadow volume. So what we have to do here is we have to count how many shadow volumes we are crossing. So don't confuse this +1 and -1 with the positive and the negative subspace. This +1 and -1 is the number of volumes that we're counting. So for example, if we're moving from here along this ray towards the object, this object here on the right, then we see we cross a front-facing volume. So we increase the counter by 1. So our counter that was initialized with 0 now becomes 1 because we add 1 here. Then we're inside of the volume until we reach this face here, which is again a front-facing volume. So we enter the next shadow volume. So we increase the counter again. So our counter becomes 2. Then we see we're moving out of this, so we're crossing another face, but it is a back-facing volume, so we know we're going outside of the shadow volume. So we decrease the counter. And then here again, we're having a back-facing volume, so we're exiting another shadow volume, so we again decrease it. Our counter, and when we reach our object, the counter is 0. That means we entered as much volumes as we exited, which of course means we're not in the shadow anymore. But for example, if we would have been here, the counter would have been 1, because although we already entered the first shadow volume, we're still a part of the second shadow volume, so we're still inside of a shadow, so we're not in the light. So the condition is basically at the end, or the condition in the end is that if we have 0, then we were either never in a shadow volume, or we entered as much as we exited, so we're in the light again. If it is positive, then we entered at least 1, maybe even more, but we did not exit all of them because we have still a counter larger than 0. So we know that there is a shadow. So this object, for example, here has a counter of 1. So we would draw this object in a shadow. Yeah. Now, the problem with this is, of course, if you do this, you have to shoot a ray towards every object. And this is pretty much the same as you do with ray tracing that we will cover after in the next week. And I already said ray tracing is not in real time. So this is something that would not work in real time. But there is a solution for this. We can use this so-called stencil buffer. And again, buffer, the term buffer, we heard that a couple of times before with frame buffer and set buffer. And again, the stencil buffer is basically the same thing, and there is also hardware support for it, of course, and it is comparable to a set buffer insofar as we have, again, basically just an image of our another array of pixels, same as in the frame buffer and in the set buffer. Only this time we don't fill it with, for example, set values, but we fill it with a counter, and you can imagine this is the counter that counts how many faces you were crossing so far. So what this stencil buffer has to support as operation, so the buffer itself is the same as a set buffer because we're just interpreting this value in there in a different way as a counter and not as a set value, but it has to support certain operations. That's what makes it then a stencil buffer, and the operations are of course resetting, incrementing and decrementing the counter, but also do it conditionally depending on a test against a set buffer, and then also do a conditional drawing depending on a test with the frame buffer, and we'll see why we need these two later operations when we look at a concrete example. So what we do with the stencil buffer, we first draw the scene only with ambient lighting, which basically means we draw it as if everything would be in the shadow. Then we compute the shadow volumes, and basically treat in the same way as we would compute the values for another object, because like in 3D this is just a cone, or in 2D it's just a polygon. And so we compute them, but we do not draw them on the screen, but we draw them in the stencil buffer. And drawing in the stencil buffer means that if we see this object here, this shadow volume, we check if the set value is smaller than the object in the set buffer. Then we check, is it a front facing? Then we increment the counter, +1. If it is a back facing, then we decrement the counter, -1. And that way we update our stencil buffer. And when we have done this with all of them, then of course the stencil buffer contains zeros for objects that are in the light, and a value larger than 0 when it is in a shadow. And of course this is intuitively clear. If you look at each pixel you would get in your set buffer, you see here that no matter in which order you check the volumes, in the end, if you always increment for incoming and decrease for outcoming, then you will in the end have a 0 if there is an equal number of front and back facing volumes in front of your object. And that is the point, in front of your object. And that is why you need this conditional drawing depending on the set buffer test, because you have to of course check if it is in front, the volume is in front, because otherwise of course you would add another shadow volume like this if you have that here, and then if you calculate that, of course you're in the shadow. But if you consider the ones in the back as well, then of course you get a wrong result in your stencil buffer. So that's why you need to do the test only to need this compare with the set value of the object. And the conditional drawing then is of course, the conditional drawing, why you need that is of course also clear, because if you have the stencil buffer filled, then you have for each pixel on the screen, you know it's in the shadow or it's not in the or it's in the light. So the conditional drawing is then, since we have it pre-drawn with ambient light, then we render the real scene, and then we say if there is a shadow in the stencil buffer, if the stencil buffer indicates a shadow, then we don't draw it, we keep the ambient light. If there is light in the stencil buffer says there is light there, then we calculate the light and draw it. That's why you need these two operations. Good, yeah, so this works quite well, but there are two basic problems with it. One is that, of course, the viewpoint can lie within the shadow. So if we have another object here, that that creates this shadow, then of course we're starting already inside of a shadow when we look towards an object. So that face is not counted, so we get a wrong result here. And the other problem is, of course, if we do a clipping and the clipping cuts off this part here that is in the direction from the camera towards the object, then also we're not covering this part here. And of course this second problem can be solved by just, when you do the clipping, just add this segment here to the shadow volume. So just change your shadow volume in a way that you have another border here. So that works quite well, but that works. You have to be careful, of course, with precision problems, like always when you deal with the near clipping plane. But that doesn't solve the problem that you have when the camera is inside of a shadow volume. Fortunately, that works quite well when we do a little modification of the shadow volumes algorithm, which is moving from a so-called death pass approach to a death fail approach. If you think about what we're doing here, we're starting here from the eye, look towards the object, and then we are counting each face that we hit and increase and decrease our stencil buffer. And then, but of course that only works if all the shadow volumes start in front of the camera. Now, and if in the end, if we have more volumes entered than we left, then we know we're still inside of volume, so we're inside of a shadow. But if we, for example, look, and that's why we don't have to look what is behind the object. But if we ignore what is in front of the object and look behind the object, we have the very same situation. If we start counting here and increasing and decreasing our buffer here, we also know, for example, if we increase by 1 here, so it's initialized with 0, then we increase it, then we decrease it, then we know now at the end we have a value that is larger than 0, so we know we entered more than we exited, so that means we should still be inside of a shadow volume. So you see, this works as well if you ignore the values here and just look at the values in the back. And that's exactly the point. If you ignore the values here, then it doesn't matter if your camera is inside or outside of a shadow volume, because you're just counting at the back. The only problem with this approach is that this here, with the near clipping plane, that same problem appears here with the front facing the far plane. If you have the far plane here and then you cut this shadow volume off, then of course you also don't see it from the camera. So that is, in that case, you also have to do this special treatment here, that you add another segment to the shadow volumes or another border to the shadow volumes. But this problem with the camera is solved by switching from a depth pass to a so-called depth fail approach. Yeah, and that basically summarizes it. Alright, so those are the shadow volumes, and the third approach that I want to talk about is the so-called fake shadows. Now, yeah, if you I mean, in graphics, it's, of course, we're interested in having the images as realistic and as natural as possible, but that doesn't mean we always have to calculate them as perfect as possible, because sometimes for people it looks very realistic, although it is actually not that perfect. And that is why, of course, in graphics we have a lot of heuristics where we just use an approach that approximates a realistic situation and then works quite well. And for example, the ambient lighting was already one of those heuristics, because it doesn't produce a perfect lighting, but it produces a pretty good results in a lot of situations, which is why at the slide I wrote it's a trick, or heuristic, depending on how you want to say it. And this is another of these approaches where we just want to apply some tricks to create a more or less realistic image with relatively low effort. And of course the name fake shadows already implies that it is not a perfectly natural situation. And the idea is that we make basically 3 simplifications of it here. So the first simplification is that we only consider a few important occluders. Now we have to decide ourselves what is important. For example, if we have this scene here with the light and the table and the glass and the bottle, if we would have a book here lying on the table, that book would also create a shadow. But if that shadow is missing in our image, we will probably not realize it that much as if the shadow of the bottle is missing. So I would say the bottle is, with respect to shadow, a much more important occluder than the book. So this is some of the decision we just make. We just remove the models that don't have a big shadow at all, that don't have a big shadow and probably will not be realized from the observer. The second simplification is that the shadows are not supported on projected on objects, but on supporting planes of, again, a few important surfaces. So we're not projecting on an object, but on a supporting plane. So for example, for the table, obviously that would be the supporting plane. So we're not projecting on a table but on a plane, which makes the calculation of course easier. And again, we're not projecting on all potential receivers but only on very few important receivers. So for example, if we look at this scene from the shadow from the bottle, we will definitely have a large shadow here. We'll probably have a little bit shadow here, but we say, okay, this is not that important with respect to the table in terms of the shadow, which is why we're not modeling we save the computation time to model the chair, but we only model the table. And this is the basic idea of the fake shadows. So it sounds really like an extreme hack, but the advantage of this is of course that there is a hardware support for it. And again, we can do it with the stencil buffer. Now the obvious problems with this is of course that the shadows, when we project them on selected shadow receivers that are plane state, for example a plane, then they have the same depth, everything. So for example, if we have a chair that is very close here, so like this, then of course parts of the shadow will in reality also fall on the chair here, but that has a different depth because we're only projecting in the depth of this plane that is in line with the table. The other, of course, even more critical problem is that the shadows might stick out. So we might get a shadow here, although there is no object here anymore because we're projecting on the plane and not on the table. And the third problem is so-called double blending, because if we project the bottle here and then we project the glass here, we have here twice the shadow, but shadows in reality don't add up. But in our image, if we do this simple hack, then we get twice as much shadow, so it gets darker, and that is also not realistic, of course. So there is not really much we can do here, but for these two here we can use the stencil buffer to solve these problems. And the idea is actually, again, quite simple. First, of course, we have to initialize our stencil buffer. Then we draw our scene, like the scene in the left image here. And when we draw a shadow receiver, which in this case is the table, then we increment the corresponding stencil buffer counters. So all the values here are 0, except for this one, which gets a value +1 here, because every time we draw a pixel from the table, without shadow, of course, so we don't have this here, then we increase it. So in the stencil buffer, we get an image like this. Now we project the shadow polygons onto this surface, so not on the table, but on the surface that is in line with the table. So we project it on this plane here, so it sticks out here. But what we do now is we check against the stencil buffer, and we can do this. We have conditional drawing in the stencil buffer. So we check when we calculate the shadow here, we check, is that point that we have in a shadow, is that actually on the receiver, or is it just on the supporting plane? If it's just on the supporting plane but not on the receiver, the stencil buffer is 0, of course. If not, it is 1, and then we draw it here. And the other thing we do here is we reset, when we draw it, we reset the stencil buffer to 0, and that way we avoid that we draw it twice, the shadow. And that is actually, that's a bad image, or there is one image actually missing here. There should be one image like this, where all of this here is larger than 0, and this here is 0, and that is the image in the stencil buffer that we get when we have drawn the bottle, or the shadow of the bottle, but not the shadow of the glass. And now you see here, because we reset the stencil buffer after we draw the first shadow, we know it when we draw the second shadow that this was already drawn in shadow, so we do not draw it again, so we avoid this double blending. Yeah, and that was the fake shadows, and that's where the three methods that I wanted to discuss with hard shadows. Of course, there's a lot more going on with shadows, and as I said, one of them is actually part of the practicals. And like I said, for the soft shadows, I don't want to go into the details here because this is much more complicated. Just like to let you know the the basic idea how it is often done is again pretty simple. If we have a single light source, a point, then of course we get this hard border here, and we can use that, but we can use that to model soft shadow by just having multiple single points here, and then calculate the shadow for each of these spotlights here. And then of course you see here that after a while you get more and more shadows here. And of course we, like I said, we don't add up shadows when we have different objects creating shadows, but in this case we can add up the shadows to calculate a factor that influences how much darker we make the color of the floor in this case, or the receiver in this case. Good, yeah, so that's the basic idea of soft shadows. Are there any questions about soft shadows, hard shadows? Other questions about the lecture? Good, then we're done for today. Remember, there is no lecture on Tuesday, so those of you who go to the DC Dark Game Jam, have fun. Those who don't, be remembered, tutorials and practicals will take place on Tuesday, so you can go there. Yeah, like I said, it's an unfortunate scheduling that we have, so just make a smart decision. And yeah, remember this cartoon that I had, less is more, so I want to see less people of you in the Herkanzing and definitely less of you next year in the course, so make sure you get your things done and prepare. All right.